It relates to the magnitude of earthquakes. So the Richter scale is a logarithmic scale where a difference in 1 unit in magnitude corresponds to a factor of 10 difference in intensity. This means that each whole number step represents a 10-fold increase in intensity. Therefore, a magnitude 9 earthquake is 10 times larger than a magnitude 8 and 100 times larger than a magnitude 7. So looking on this Richter scale, a few earthquakes are listed here. The 1976 earthquake in Italy, which is here, had a magnitude of 6.5, was how many times as intense as the 1983 earthquake in Colombia? So this has a difference of a 1 in magnitude. So the earthquake in Italy was actually 10 times as intense as the earthquake in Colombia. In 1993, the earthquake in Japan hit a 0.9 on the Richter scale. Was how many times as intense was the 1966 earthquake in Turkey, which was 6.9. So technically, this is a difference of 2 in magnitude, which is technically 10 squared or 100 times as intense. Okay. So how do we compare intensities of magnitudes M1 and M2 that do not differ by integer values? So the magnitude of an earthquake is given by the following formula. M, which represents your magnitude, equals the log of I over I subscript 0, where I is the earthquake intensity and I subscript 0 is a reference intensity. And technically our reference intensity would be always represented as a 10-fold value to the power of 0. So technically 10 to the power of 0 is 1. So this reference intensity really always represents a value of 1. Okay, so it really has no effect of the formula. It's just always in the formula. So if we're given a magnitude 1 of log of intensity 1 over reference intensity, and magnitude 2 is equal to log of intensity 2 over reference intensity. If I wanted to compare these two magnitudes, so if I were to subtract these two magnitudes on my Richter scale, I would technically want to subtract these two logarithmic equations. And so when I do that, I'm going to now simplify to get a more simplistic equation that I can use to compare any two magnitudes. So M1 minus M2 is going to be equivalent to, I'm going to use my quotient rule here to separate this. So this would be a log of intensity 1 minus log in reference intensity minus, I'm going to do the same thing here, log of intensity 2 minus log of reference intensity. So now if I run this negative through my set of brackets, I get log intensity 1 minus a reference intensity minus log intensity 2 plus our reference intensity, because I'm running that through my set of brackets. So what's going to happen is these reference angles actually end up canceling, and what we're left with is log of intensity 1 minus the log of intensity 2. Again, I'm going to combine these now as a single logarithm by using my quotient law. Okay, so furthermore, if I wanted to go further now, I'm going to change this back to an exponential function. So the base of my logarithm is 10 to the power of m1 minus m2 equates to the comparison of my intensities. So this is a formula that we want to...
Good morning, Beth Basie. Can we please get a janitor to the office? Janitor to the office. Thank you.
This is a formula we want to refer to over and over again in terms of Richter scales, and we're going to get into loudness of sound and even pH level. This is not on your formula sheet. So what this is saying is all that we're doing here is we're taking the intensity of 1. If we took the intensity of one earthquake, divided it by the intensity of a second earthquake, technically that would give us 10 to the power of the difference of our magnitudes. So I'll show you what I mean by that. So how many times more intense was the 1985 Mexico earthquake in 1966? Well, Mexico hit a Richter scale of 8.1. And versus the Turkey earthquake, which hit a Richter scale of 6.9, or 6.9. Okay, so Mexico was 8.9, Turkey was, Mexico was 8.1, and Turkey was 6.9. So technically, if I wanted to compare these intensities, intensity 1 divided by intensity 2 would technically be 10 to the power of 8.1, that's my Mexico intensity, divided by 10 to the power of 6.9. Well, what do we do when we divide exponents with common bases? We subtract those exponents. So this would be equivalent to 10 to the magnitude of 1, which is 8.1, minus the magnitude of 2, which is 6.9. So technically, in order to compare the intensities of two earthquakes, we just need to take 10 to the power of the difference between those two magnitudes, which would give us 10 to the power of 1.2. So if I calculated this, 10 to the power of 1.2 would be 16 times more intense. So the Mexico earthquake was 16 times more intense than the Turkey earthquake. All right. All right, example 2, it says a major earthquake of magnitude 7.5 is 700 or 375 times as intense as a minor earthquake. Find the magnitude to the nearest tenth of the minor earthquake. So what two things am I comparing here? I'm comparing the intensity of the major versus the intensity of the minor. And I know that's going to be equivalent to 10 to the power of magnitude 1 minus magnitude 2. So technically, the comparison of these two intensities would equate to 375. I know the intensity of the major earthquake was 7.5. And then we're trying to solve for our second magnitude. So how would we solve this equation? So in order to solve this equation, because I can't get a common base between 375 and 10, I need to use logarithms to solve this. So I'm either going to change this to logarithmic form or simply take the log of both sides of the equation. Okay? If I took the log of both sides, change this to a logarithmic form, it would be log base 10, which I don't need to write, of 375 equals 7.5 minus magnitude 2. So technically, our second magnitude, if I take the log of 375 minus 7.5, that's going to equal negative m2. If I calculate that, so on my calculator, if I take a log of 375 minus 7.5, I get negative 4.925, or negative 4.9 is equal to a negative m2. So technically the magnitude of the minor earthquake would be on a 4.9 on the Richter scale. Okay. All right, so that's Richter scale. The next thing we're going to talk about is loudness of sound. Loudness of sound is currently measured in decibels, which is equal to 1/10 of a bell. So we want to think 10 decibels is equivalent to 1 bell. The decibel scale, like the Richter scale, is a logarithmic when the difference of 10 decibels corresponds to a factor of 10 difference in loudness of sound. So a leaf rustling, which is 10 decibels, is 10 times as the threshold, is 10 times as loud as the threshold of hearing. So threshold of hearing is like our reference intensity or reference sound, which again is a 10-fold value. So this would be 10, technically 10 to the power of 0. A whisper, which is 30 decibels, is 1,000 times as intense or as loud as the threshold of hearing. So 30 decibels really relates to 3 bells. So this would represent 10 to the power of 3 in relationship to this. So 10 to the 3 would be 1,000 times louder. Okay, so complete the following. A power saw of 120 decibels is how many times as loud as a telephone dial, which is 80 decibels? Well, technically, a power saw would be 12 bells. The telephone dial would be 8 bells. So the difference between these two values would be 10 to the power of 4. Everything is a 10-fold difference. So this would be 10 to the power of 4, which is 10,000 times as loud. So a power saw is 10,000 times as loud as a telephone dial. A whisper is how many times as loud as a conversation. So I'm comparing the whisper to a conversation. The conversation is louder. So again, the conversation is represented by 6 bells. A whisper is represented by 3 bells, which would be a 10 to the power of 3. But we're comparing whisper to conversation. So it's going to be 1 over 10 to the power of 3, which is 1/1000th. So 1/1000th times as loud. Okay, so it should be a smaller value. All right, so similarly to compare loudness, intensity of 2 sounds measured in bells, same as the Richter scale, is if I'm comparing 2 intensities, it's going to be the exact same formula. But remember, we want to convert this into bells. So you noticed I don't want to subtract 120 from 80 here. I subtracted 12 from 8 to get my exponent value on 10. So same sort of idea. If I'm comparing 2 loudnesses of sounds, this is going to be 10 to the power of the bells of first loudness minus the bells of the second loudness. So how many times more intense is the sound of a piano playing, which is 67 decibels, than a whisper, which is 22 decibels? So 67 decibels would equate to 6.7 bells, and 22 decibels would equate to 2.2 bells. So if I'm comparing the piano to the whisper, I'm simply going to take 10 to the power of 6.7 minus 2.2, which gives me 10 to the power of 4.5, which equates to 31,623 times as loud. Okay. All right, next example. It says 2 telephones in a home ring at the same time with a loudness of 80 decibels each. Does this mean that the total loudness of sound would be 160 decibels? Would I add those 2 loudnesses? Well, when you think about, right, this scale, 80 decibels is the loudness of a telephone dial. If I added that to make, because there's 2 of them, to be 160, that sound would be louder than a jet engine. It would like pass this decibel scale. So it's pretty obvious that by adding the 2 decibels is an incorrect method, because your house isn't going to be louder than a jet engine. Okay, so how do we figure this out? What would be the loudness of 2 phones ringing at the same time? It's definitely louder than 80 decibels, but probably by not much, right? So if we think of the intensity or the loudness of this, of one phone in relationship to the threshold of hearing would be 10 to the power of 8. Right? Because this would be 8 decibels. Okay? And so what do I want to figure out? And technically I want to multiply this loudness by 2 because I have 2 phones. So what would that equate to? What would be my new bell value as for 2 phones to be ringing? So what I'm going to do is I'm going to equate this value, right? So 2 times 10 to the power of 8 equates to 200,000 equals 10 to the power of x. I now want to change this to, if I'm solving for x, I'm going to change this to a logarithmic form. So log base 10 of 200,000 is going to equal x. So when I calculate that, log of 200,000 works out to be 8.3 bells. Okay, so therefore 2 phones ringing together would have a loudness of 83 decibels, right? Because 8.3 bells, we multiply that 10 to change it to decibels. Okay, all right, so that is an overview of loudness of sound. And then the last thing you might come across is our pH scale. So the pH scale measures the range of hydrogen ion concentration by determining the acidity or alkalinity of a solution. The scale measures from 0 to 14, with values below 7 represent increasing acidity and values above 7 representing increasing in alkalinity. The value of 7 represents our neutral level on the pH scale. Okay, so that's like our our reference intensity in a way. Similar to the Richter and decibel scale, the pH scale is a logarithmic where a difference in 1 unit of pH corresponds to a factor of 10 difference in intensity. This means that each whole number step represents a 10-fold increase in intensity. Okay, so if 7 is our neutral point, right, all of these values would be the increasing alkalinity. Going to the left would be increasing acidity, where 7 is our neutral point. So tomato juice is, sorry, this should read lemon juice. Is how many times as acidic as pure water. So here's our lemon juice is at a value of 2, and so how many steps over is it compared to pure water? 1, 2, 3, 4, 5. So this would be 10 to the power of 5, which is 100,000 times as intense. Okay, milk of magnesia, which is at an 11 on our pH scale, is how many times as what as, and this shouldn't say blood, sorry, these are typos. We will say seawater. And I think seawater is at, let's say seawater is at an 8. Okay, so milk of magnesia is, it's 1, 2, 3 steps over from seawater. So this would be 10 to the power of 3, which is 1,000 times as alkaline as seawater. Okay. So once again, to compare acidity or alkalinities of one solution to another, again, same as our Richter scale. If I'm comparing those two acidities or alkalinities, we're going to take 10 to the power of the pH of one versus the pH of the second one. All right, so it says pure water has a pH of 7. Swimming pool water has a pH of 7.5. And seawater has a pH of 8.4. How many times as alkaline is seawater to pure water? So I'm comparing my seawater alkalinity, which is 8.4, to the pure water. So if I'm taking seawater to pure, I'm simply going to take 10 to the power of 8.4 minus 7, which is going to be 10 to the 1 decimal 4, which works out to be 25 times as alkaline.